Let's talk coral. Coral reefs are in danger all over the world, and because they are the foundation of entire reef ecosystems, they're essential for about a quarter of all marine life. Most people know that reefs are bleaching, and that a major cause of coral bleaching is the increase in ocean temperature due to climate change. Less commonly known are the host of other risk factors, from organic compound-based sunscreens to sedimentation caused by farming practices. By the way, your organic chemistry professor called. He wants you to choose inorganic zinc oxide-based sunscreens. But today we're going to talk about equilibrium, which in turn will help us to understand how the increase in atmospheric carbon dioxide affects the dissolved carbon dioxide and in turn the carbonate-based creatures like corals' ability to build the calcium carbonate skeletons. The Analytical Chemistry 2.1 text actually has a really nice context for equilibrium that's closely related. Our story begins, as these stories often do, with a young and up-and-coming politician. He's not a deeply religious man and a member of the Revolutionary Party. He's completely single-minded in his convictions and has no regard for the political process. Eventually, his party launches a special project in the name of national security. While I hope at least some of you are thinking of Adam Sutler from V for Vendetta, I'm actually talking about Napoleon, who launched his career with a military expedition to Egypt at the end of the 18th century. Napoleon brought over 100 members of the Commission of Sciences and Arts, including chemist Claude Berthollet. Claude made a trip to the Wadi el-Natrun, the Valley of Natron, where natron, also known as sodium carbonate, was harvested by the Egyptians. If you pay close attention, you might notice that natron sounds a lot like natrium, which is actually the Latin name for sodium, and the source of the Na symbol. But I digress. All the cool scientists at the time said that every time things reacted, they reacted completely and irreversibly. That's because that's all they've observed. And one well-known reaction was that sodium carbonate, again, that's known as natron at the time, would react irreversibly with calcium chloride to precipitate lime, also known as calcium carbonate. People did this in the lab all the time. It was real, it was fun. It wasn't real fun. But when Claude looked at the waters that were in contact with limestone around the Wadi el-Natrun, which is functionally made out of lime, calcium carbonate, he found that crystals of sodium carbonate would form at the water's edge. He didn't see those crystals where the water was against clay, which suggested that the lime, calcium carbonate, was actually reacting with the salt water to form natron. Claude realized that the contemporary scientific conception of reactions in one direction was wrong, and that it sat on a throne of lies. Instead, he suggested both reactions proceed simultaneously, as shown by the forward and backward arrows in the third reaction, until finally the rates of the reactions became the same and the concentrations became constant. This explains the previous observations for the rapid formation of calcium carbonate observed in the lab, the top reaction. The reaction with calcium chloride is very fast and nearly complete when the sodium levels are low and the calcium levels are high. But the calcium levels will eventually fall and the carbonate can be leached back out of the solution by salt. This observation paved the way for the entire field of thermodynamics, which is the study of reactions that are controlled by equilibria. Central to this study is the idea of free energy, the potential of a chemical system to do work. The free energy equation shown defines the capacity for work, delta G, in terms of the stored heat energy within bonds, the enthalpy, given as delta H, and the temperature, given as T, always in Kelvin, and the dispersion of energy given as delta S, the entropy. The delta S is always positive for the universe. If the capacity for work goes down, that is, the delta G is negative, the reaction will occur spontaneously. We can think of delta G as a sort of total potential energy. If we look at the reaction diagram on the left, we might start with a high potential and end with a low potential. This reaction is called exergonic. The delta G is negative and the reaction happens. If we look at the reaction on the right, the potential increases in the reaction, meaning the delta G is positive and the reaction doesn't happen, at least not under standard conditions. There are a few things that can change those conditions and actually change whether a reaction will occur or not. First, if you look really carefully at the equation, you'll notice that if delta S is always positive, the higher the temperature goes, the more likely we are to have a low or negative delta G. So higher temperatures will generally make reactions more spontaneous. But you know that already because when we want a reaction to occur faster, we just heat it up. The delta H and the delta S values are also specific to reactions, so the relative values will help determine whether a reaction goes. But again, you knew that there are reactions that go and reactions that don't. So it's no surprise that the underlying energies and entropies are reaction specific. Perhaps the most important, though, is that the concentrations of reactants can actually change the equilibrium. That's how your body gets reactions that aren't very favorable to occur. You increase the concentration of those reactants until some product might be formed, some small amount of product, and then you keep the product concentrations low by quickly reacting them away. Hopefully you saw that or will see it soon in Biology 306. The root of this change comes from the fact that delta G is always a function of a standard condition delta G, indicated by delta G0. That's the one under standard conditions, which, for example, include everything as 1 molar concentration and the actual conditions in a system, which are actually different in most cases. We represent those by the term RT natural log of Q. In this term, R is the gas constant, and T is the temperature in degrees Kelvin, and Q is the reaction quotient. We'll talk a little bit more about that in a second. When the RT natural log of Q term is equal in magnitude but opposite in sign to the delta G0, when those essentially cancel out, the overall delta G will be 0 and the reaction is at equilibrium. This reaction quotient is really just a ratio of the product concentrations in a reaction raised to their coefficients over the reactant concentrations raised to their coefficients. Solids and solvents aren't included in these calculations, and gases are always included as partial pressures. So if a reaction like the one that our friend Claude Berthollet discovered was described, the reaction quotient would be the concentration of sodium chloride over the concentration of sodium carbonate or natron times the concentration of calcium chloride. The calcium carbonate, the lime, is not included because it's a solid in this reaction. Since every coefficient is 1 in the reaction stoichiometry, the powers for each concentration are also 1. Remember that this reaction quotient is a function of the larger equation for delta G. When delta G is 0, that is, the reaction is at equilibrium, the equation simplifies to delta G 0 equals negative RT natural log of Q. Now think about the math just for a little bit here. Since the products are on the top of the Q, that means that the more products that there are relative to the amount of reactants, the larger the Q value will be. A Q value greater than 1 will result in positive natural logs, meaning that the overall sign of negative RT natural log of Q will be negative when there are more products than reactants. All that math means that a negative delta G0 implies a product favored reaction. Negative delta G means more products form. We can solve for exactly how much the reaction favors products by defining the Q when the reaction is at equilibrium as an equilibrium constant Keq. Notice just one more thing with me. I promise just one more thing. The presence of the temperature T in this equation means that the actual point of equilibrium is temperature dependent. Just to recap, we can define the relative concentrations of products to reactants at equilibrium as the Keq, the equilibrium constant. This is temperature dependent. Being able to define equilibrium concentrations of different ions, atoms, and molecules is incredibly useful for understanding what's going on in solution. So let's look at our Keq for our specific natron and lime precipitation reaction again. The Keq would be positive because the reaction, as observed in the laboratory all the time before Claude made his natron lakes trip, always proceeded spontaneously, so we know it's product favored. If If we think about the reverse reaction, the one that leaches out natron from the lime, we'd actually have the KEQ flipped. The natron and calcium chloride would be on top instead of on the bottom, and the KEQ would be less than 1. It would favor the reactants. If we have more than one KEQ for multiple reactants, we can actually combine the KEQs in order to combine the overall reactions. So let's think about how this worked. Suppose we wanted to form calcium carbonate, but instead of having sodium chloride, we just had baking soda in our kitchen. Or this reaction might be then sodium bicarbonate or baking soda plus sodium hydroxide yields sodium carbonate and water. The equilibrium constant for the reaction would have the sodium carbonate on top and the sodium bicarbonate and sodium hydroxide on the bottom. Water is a solvent for the reaction, so it isn't included in the equilibrium constant. We can add the two reactions together, and when we add them together, reactants and products will cancel each other out and leave the overall reaction as shown. Notice that this reaction has the equilibrium constant, sodium chloride over calcium chloride times bicarbonate times sodium hydroxide. This is the exact same as the product of the equilibrium constants of those two reactions. Whenever we add reactions together, we can just take the product of their equilibrium constants. There are a number of equilibrium constants that have special definitions. The first of which is the solubility product, Ksp. When a solid dissolves into a solution, there's a limit on how much of each ion can be dissolved, defined by the solubility product. But because the reactant is a solid, the equilibrium constant has no reactant in the denominator. And so the equilibrium constant is just the product of the dissolving ion concentrations, a solubility product. The relevant solubility product for calcium carbonate is 3.3 times 10 to the negative 9th. So we'd say that this is very much reactant favored because it's a very low or very much less than 1 value. Write that value down because we'll actually use it later. Water has its own special constant called the Kw. It's the equilibrium constant for water splitting up into an H+ and a hydroxide. At 25 degrees, the temperature that most equilibrium constants are reported at in chemistry, the Kw is equal to 1.08 times 10 to the negative 14th. As a side note, in most cellular biology contexts, the equilibrium constants are actually reported at 37 degrees, approximately human body temperature. Another really relevant equilibrium constant for this carbonate system is the Ka, the acid dissociation constant. The Ka is the equilibrium constant for an acid separated into H+ and the conjugate base. You can see two examples shown for bicarbonate dissociated into H+ and carbonate, or carbonic acid dissociated into H+ and bicarbonate. Even though we could also talk about the base association constant, the Kb, where we grab an H+ from water to make hydroxide, chemists actually never report the Kb. That's because the Ka and Kw together can always give us the Kb, and so it's almost completely redundant. Like when we talked about pH before, we often report Kas as the power function, so we can take the negative log of Ka to find the pKa. If we want to use the pKa in an equilibrium context, we just have to go the other way. We take 10 to the negative pKa to give a Ka. The Ka equations that are given are also really important for understanding coral bleaching because they relate to the concentrations of carbonate which corals use to make their calcium carbonate skeletons, with bicarbonate and carbonic acid, which are other related forms in water. So the pKa of the top relationship is 10.3 as shown, and the pKa of the bottom relationship is 6.4. Because pKa's are the negative logs of Ka's, the higher those numbers are, the more they are reactant favored. This means that the dissociation of bicarbonate to carbonate is far less favorable than the dissociation of carbonic acid to bicarbonate and H+. And that makes sense because carbonic acid is called an acid, so you would expect it to want to dissociate. Write down these pKa's that are shown, the pK of 10.3 for bicarbonate dissociating, and the pK of 6.4 for the carbonic acid dissociating before we continue. I'm going to give you a problem to work on with these two values in 3 slides. If I have a whole list of pKa's, and I know that I've got a solution at a particular pH, how do I know what form a given substance will most take? Like, do I expect to have more bicarbonate or more carbonate in my solution? One way to quickly look at that relationship is by taking the negative log of the whole Ka equation, the one that's shown kind of in the center. If we take the negative log of the whole equation, this relates pKa to the negative log of the H plus times the A minus concentration over the HA concentration, as shown. With logs, you can pull things out that are multiplied inside the log as something added outside the log, which is what we've done here. That allows us to separate the negative log of H plus concentration, which you might recognize as pH. We're able then to make a very quick comparison between the pKa and the pH. If the pKa is greater than the pH, we would expect that the negative log of A over HA would need to be positive. We'd need a much larger denominator than numerator, and so we'd have more in the acidic form than the basic form. Again, that's if the pKa is greater than the pH. That makes sense because if we have a lower pH than pKa, that essentially means that we have more acid than we need to be at equilibrium, and so it's no surprise that we have more of our analyte in acidic form. If the pH is greater than the pKa, the log actually needs to remain negative, which happens when there's more base than acid. So pKa's can be very useful benchmarks for us to know what form our acids can take. The equation that's shown at the bottom, by the way, is called the Henderson-Hasselbach Equation, and we use it all the time for buffers. The Analytical Chemistry 2.1 text uses these pKa values in a very helpful and descriptive fashion called a ladder diagram. The pH is placed on a vertical arrow. The pKa for any acid is placed on an arbitrary labeled point along the line. Any place below this pKa is more acidic than the equivalence point, and therefore is going to be dominated by the conjugate acid in the equation. So here we show a relationship between acetic acid and acetate, and we see that below the pKa of acetic acid, we see mostly acetic acid. Any place above the pKa is more basic than the equivalence point and is therefore dominated by the conjugate base in the equation, in this case acetate. This not only helps us get a picture of individual species in solution, but it can also be really helpful for understanding multiple species on the same diagram. You can easily see what pH ranges would give both conjugate bases, which pHs would give a mixture, and which pH ranges would give only the acids. We can even put multiple pKa's for a polyprotic species. For example, sulfuric acid has the lowest pKa for the most acidic proton, and that goes towards the bottom. Below that line that we just drew, at pH negative 2.8, we have almost entirely sulfuric acid, and above that line is bisulfate. And the next pKa comes, and once we're above that line, we get to sulfate. So we really only see bisulfate when the pH is between negative 2.8 and 1.99, and when we become above around pH 2 or so, practically all of the sulfate-related compounds become sulfate. You can see that very quickly from the diagram. So now it's your turn. See if you can draw a ladder diagram for the carbonate system, the one that we care about for coral, and then check your work against the textbook example 6.5. We've now worked through solubility products, which are Ksps, the water constant Kw, and also acid dissociation constants Kas. There are also partitioning constants between phases, the most important of which are the Henry's law constants. Henry's law is essentially the equilibrium for a gas to dissolve in water, and so it always has the concentration of the dissolved gas over the partial pressure of the gas in its form. So the Henry's law constant for the carbon dioxide dissolution is 3.4 times 10 to the negative second moles per liter atmospheres. Whenever we're using Henry's law, we need to be really careful with units. While every concentration is an aqueous solution is going to be given as a molarity, pressure units for gas phase partial pressures can vary. If we want to use a Henry's law constant that has atmospheric units like what we have here, we need to make sure that our pressure is in atmospheres. Otherwise, the math won't work out. Carbon dioxide goes through another reaction in water as well. It actually quickly combines with water to become carbonic acid, which has its own equilibrium constant of 1.7 times 10 to the negative third. It's somewhat common to just multiply the Henry's constant by the carbonic acid forming equilibrium and combine those KEQs, but that actually glosses over the significant amount of carbon dioxide that might form in, say, the ocean, as we're also making carbonic acid. So maybe you can see where we're going with this. We should be able to use the equilibrium constants to figure out how much carbonate is present in an ocean at equilibrium with 400 parts per million carbon dioxide, or whatever we get to, and what that means for the free calcium concentrations available to our corals. We'll actually do that together in class, and then we'll have Nick call up Summer Brosio to see if she knows what calcium concentration the corals actually need to survive. Hopefully it's good news. I'll also teach you a trick in Excel, so if you bring your computer, you can follow along in Excel as well. We'll talk about metal availability depending on what ligands are available, both in environmental chemistry and in quantitative analysis. When metals coordinate with ligands, we call that a formation reaction, and we can talk about specific formation constants, or KFs. As a side note, biologists talk about these complexes breaking down instead of forming, and so we talk about the reverse reaction in biology. So biologists will use a dissociation constant, a KD, instead of a KF. The KD is just 1 over the formation constant, or vice versa. The formation reactions actually happen in steps, just like acid exchanges. And so we can construct ladder diagrams for individual additions of ligands, like we have done for additions of individual protons for polyprotic acids. Instead of a pH, we put the power of a ligand on the arrow, which means that the lower number would mean more ligand, and the higher number would mean less ligand, just like a lower pH means lower hydrogen, or means more hydrogen. You can see this for the cadmium and ammonia system, that at the very top of the graph, where there's little ammonium, cadmium's mostly free. It's not bound to anything. But once you fall below the power of ammonia of 2.55, there's a pretty narrow range where the cadmium isn't completely covered with ammonia, and it very quickly happens to the point where it's completely covered below a power of ammonia of 0.84. This can also be really helpful for competitive binding. In a system with both calcium and magnesium, a ladder diagram using the formation constants with the ligand EDTA gives us a clear indicator that the calcium will be bound up with the EDTA much more readily than the calcium. So it happens at a lower concentration of EDTA, allowing us to have solutions that have just magnesium, but not the other way around with just calcium. These diagrams can also be really useful in redox calculations, but first let's define a few of our redox terms. If delta G is the capacity to do work, electrical work can be calculated based on the number of electrons, which we give by N, the charge of electrons, which we get by F, which is Faraday's constant, and the potential, which we give as E. Just like the delta G is affected by the actual relationship of the reaction conditions to equilibrium, the reaction quotient, we can define the redox potential in terms of the same relationship. By convention, we simplify the resulting equation to be in terms of E and E standard. And then we'll simplify all those constants. That's the gas constant, the R, the Faraday's constant, F, the temperature, which was pretty much always 25 for these types of reactions as we do them in lab. And even we simplify out the natural log because powers of 10 are just easier. And we put all of that in a single value of 0.05916. So that just comes from taking the values of all those constants. Just like delta G standard, E standard is 0 when we're at equilibrium. So this E value for redox potential is essentially a measure of free energy and the spontaneity of the reaction. But because E has the opposite sign from delta G, which you can see a little bit easier at the very top, reactions are spontaneous when the redox potential is positive, as opposed to delta G, which is spontaneous when the sign is negative. When we talk about redox reactions, we don't have equilibrium values for the entire reactions, since there are so many mix and matches possible. Instead, we always report half cells, literally only half of the reaction, and then we combine those half cells. Non-redox active species like H+ can get added to the balance as needed. We don't have to worry about those. These are always normed against a standard reaction, since we can't actually measure just one half cell. So our zero potential reaction is the reduction of 2 hydroniums to water and H2 with a platinum catalyst, a setup called the standard hydrogen electrode, and everything else is going to just be relative. We can find all sorts of tabulated values for E's of half cells compared to that standard hydrogen electrode in Appendix 13 of the Analytical Chemistry 2.1 text. It's on page 1071. In the PDF, that's 1095 out of 1122. Anyway, this can be really useful for reactions that involve redox. For example, the combination of nitrogen and hydrogen to produce ammonia. This is actually the second largest human chemical production, as the ammonia is used for fertilizer for food production. This reaction can be split up into 2 parts, the reduction of nitrogen to nitride and the oxidation of hydrogen to H+. Notice that the reaction that I just put up is actually backwards. It shows hydrogen reduced rather than oxidized, right? Because the hydrogen starts out as plus and actually becomes oxidation state 0 as its elemental form. That's because all the standard potentials in tables are as reductions. If we want the oxidation instead, where hydrogen becomes more charged, we'll just take the opposite of the value for E. Here it's a little bit silly because it's a 0 anyway, but I hope it gets across the point. Typically, these reactions are performed in acidic solutions, which help to facilitate the reactions. In acidic solutions, nitrogen doesn't become nitride and instead becomes ammonium. It's the same extent of reduction, but with the acidic hydrogens to balance. So this reaction that's shown on the bottom is the actual reaction that we can look up. We can't look up the N2 to 2 nitride reaction. So if we wanted to find the actual reaction potential for this nitrogen becoming ammonia, we'd actually use the 2 values that are shown. We'd take the, we'd subtract the -0 from 0.274, and we'd end up with 0.274 as the overall reduction potential. Just as before, ladder diagrams can give us really helpful qualitative descriptions about what's going on in solution based on the potential of that solution. So we can plot the redox potential, E, now on the line, and we'd put the standard half cells for each redox that we're interested in along those lines, just like we did for pKa values. So if the standard redox potential for tin 4 reducing to tin 2, which is shown on the right, tin is SN if you don't recognize that. If we have that at 0.154, anything above that is likely to have more tin 4. It's likely to be more oxidized. And anything below that will have more tin 2. It's more likely to be reduced. And we can compare the redox potentials of 2 species. We can see that the iron on the left side reduces at a higher potential than tin, which means that we could have reduced iron while still having oxidized tin, but not the other way around. This can be really helpful for understanding how metals might change. for example, at the bottom of a stream bed instead of the surface water.